All right, guys. Welcome to Lab 1. My name is Alano. My Panther ID is 6306968. This is course number EEL-3110C. And we're a group 10, and we're doing the Lab 1 project presentation.
Hi, my name is Moncrieffe. My Panther ID is 6264565.
All right. Hi, my name is Rojas-Perez. My Panther ID is 6186196.
The learning objectives for this lab is being able to construct a series parallel DC resistive circuit and being able to get familiarized with the multisim software application. We need to get familiarized with running the constructed simulation to see the variable changes of the electricity flowing through the circuit, measuring the effect of each element in the circuits, and observing the electrical numerical results. Comparing the value from the simulation to the hands-on theoretical calculation, such as KCL, KPL, and the Ohm's law.
All right, so this is activity 1. Its main objective was to basically expose us to multisim and how it works. So here we have an open circuit with a voltage source of 4.2 volts and a resistor with 2.7 kilo ohms. And on the following slide, here we follow the directions given to us in activity 1. And we went ahead and located the 2 probes on point AD. And we had a source of 4.2 volts. On VAB, it should actually be 0 due to the fact that it's an open circuit.
So activity 2, it asks us to construct a parallel circuit. It seems like on the left side, you're seeing a closed circuit, but on the right side is an open circuit. For this activity, it wanted us to, or we chose to have a 4.25 volts as our source and a 3.3 kilo ohm resistor for our R1 and a 6.60 kilo ohm for our R2. You can see over here, the lab wanted us to measure from various points. Voltmeter VAD is getting 4.25 volts, and that makes a lot of sense because that's a closed circuit. And if we were to apply KBL, then we must have all of the voltage drop across those resistors. VAB is getting 0.801 millivolts, which pretty much is non-existent. It's supposed to be actually be 0. From my understanding, it might be a software glitch, or it could be a leakage current that's coming out of this wire, since if you're seeing this wire is still connected. Here is the hands-on calculation that we got. If you were to compare that to the measurement that we got from the simulation, we pretty much have the same value.
All right, so for activity 4, so here we have a closed circuit. We have 2 resistors. One divided the 1.00 milliamps by the source. This is basically the hands-on calculation. So EEL's law. So we are basically isolating I. We have the voltage source plus the 2 resistors, and everything is equal to 0. So we charge is equal to 1 milliamp, and following Ohm's law which is 12 volts. So plug in the values, and it equals out to 12,000 ohms.
Again, this is a series circuit with 12 volts, with 2 kilo ohms and 10 kilo ohms in series. When we put the probe across the initial section, we get 12 volt because there's no load across that. That's the load for the battery. And we went ahead and put the probe across R1. And when we did across R1, we get 1 milliamp. And we proceed to do it across R2, where we get 10 volts. So there's 2 volts for R1 and 10 volts for R2, which equals to a volts of 10 volt that is equal to the battery that's being used. Consideration of using a probe, we did a algebraic calculation of to correspond with the initial value that's given from the probe. And as you can see, using the KVL law, we know that the voltage across the entire circuit is equal to 0. So when we did the calculation, we know that resistance is equal to voltage over current. So we did VAB, we realized that it's 12 volts over 0.003 amps, which equal to a total of 4,000 kilo ohms, or 4,000 ohms, which equal to the total resistors that is in the circuit.
We have a parallel circuit. It wants us to have a resistor R2 for condition A that is way less than R1. The initial measurement that the activity wants us to get is the total resistance between point A and point B. Since I know the total current, all I have to do is use Ohm's law and divided the voltage source to divide it to the total current, and that would result into 740.7 ohms. Here's the activity 6 condition B. Pretty much the same process, following the same process as I did or we did earlier, in order for us to get the total resistance. If we look at here, we did the KCL, the KVL again, and we get the total current of 30 milliamps. In parallel circuit, that we're gonna get the same voltage across the branches.
In conclusion, current, when we did all the calculation, we found out that current in series wire will always be the same all across the circuit. As for the voltage, the value in parallel circuit has the same value for each branch as seen in the previous slide that was done. Theoretical calculation using KVL, KCL, and Ohm's law matches the value in the computer simulation. Thus, these laws hold strongly through application. Thank you.